So I would like to thank the organizers of this conference for the honor of being one of the speakers. So I'd like to talk about perhaps some ideas involving the interaction of dynamical systems and Diophantine questions, Diophantine problems, and try to say where it succeeded and where it hasn't succeeded, and what ideas may be useful to push this connection forward. As far as the basic definitions, a dynamical system means that there's some sort of a space, X, and a transformation, sometimes invertible, sometimes, but not necessarily, of the space X. And to say that you're talking about dynamical systems means that you're really interested in what happens as you iterate the transformation. For example, you're interested in asymptotic behavior of the orbits. You look at all the Tn, t raised to the n of x for n over the integers or over the non-negative integers. Where x is a space, in many situations it'll be a manifold. In classical situations, it's a manifold. You can generalize and speak about topological spaces. Very often, most often, one is interested in compact spaces, but not necessarily. And there may be some other structure, and particularly maybe talking about a measure space. At any rate, it becomes a dynamical system because you're interested in iterating the transformation. Or you may have some more general group or semi-group of transformations on the space. Now, the connection with Diophantine problems comes about the following way. Suppose I have a dynamical system, and we pick a point x naught, and we look at the orbit of x naught, and suppose we have some function, and usually it'll be some, say, continuous function, and not a completely arbitrary function on the space, so we can evaluate the function on the orbit. And so we get a sequence xi of n, and presumably the sequence xi of n, which may be of interest for number theory, presumably a sequence xn somehow reflects the dynamics of the original system, some form or other. Now, now in some sense, there is a way, I mean, to say that a sequence comes about in this way is not saying very much, because indeed every sequence can be represented this way. In particular, if xi of n is bound, if I have some bounded numerical sequence, there's a standard way of finding a compact space, a homeomorphism of the space, it'll be a metric space, and a point x naught, so that the given sequence has this form. It's like reading some parameter over time in this dynamical system. So every sequence can be represented this way, and the basic approach, which I'll be talking about today, sometimes it works, sometimes it may not give anything. Basic approach is that we're given the sequence, and we want to study the sequence. We want to think of the sequence as being generated by a certain dynamical system. Then we want to make use of the properties of the dynamical system to study the sequence. This reverses something that took place very early in the theory of dynamical systems. I mentioned the name of Bebutov theory, of the notion of a Bebutov system, at a very early stage when people had no idea of what kind of general dynamical systems were really possible. So they formed sort of artificially dynamical systems by starting with very arbitrary sequences. And using properties of the sequences, they found out properties of the dynamical system. In other words, how much periodicity forces, how much almost periodicity would force periodicity, things of this type. And these were answered by using sequences to study dynamical systems. But what we want to do is move in the opposite direction. Here's an example, a theorem which is not very difficult, but this is a theorem which illustrates, to my mind, it illustrates well why it should be that if we're starting with something fairly simple-minded, a sequence of numbers, what can be simpler than that, and we're converting it into something complex, something sophisticated. We have a dynamical system and looking at the behavior of the dynamical system. Why should it be that that would help? So here's a theorem which generalizes this well-known fact that was originally proved by Hardy and Littlewood and then proved a much stronger version by Weil, that say that if alpha is an irrational number, then n squared alpha is dense modulo 1. Fractional parts of n squared alpha fill the unit interval. Now, generalization, I mean, that will be a special case. It's a special case of many theorems, but in particular the following theorem. Suppose I have a continuous function on the reals, which is not quite periodic. I mean, f of t plus 1 is f of t plus some fixed integer, but non-zero integer. Then if we form these partial sums, f of alpha plus f of 2 alpha up to f of n alpha, and look at that sequence is always dense modulo 1. It's easy to see that if m would be 0, that needn't be true. Excuse me? M is not 0. I'm sorry, alpha is not in Q, right. Right, there is another function that needn't satisfy the theorem. Okay, so so you have we have a particular sequence. I'm giving here. I'll give a sketch of the proof in order to explain this idea of how the global dynamics is helping you study a particular sequence. You may be interested in this for a very particular case, but you won't see what's happening really just by looking at that one case, and you really have to look at something globally. So we take the sequence. We take our sequence C of n to be the sequence that we're looking at. Although actually I want to look at it not in the reals, but in the reals modulo z, modulo 1. So Cn is really the sequence on the circle. If you follow this natural procedure for getting a dynamical system that generates the sequence, you'll find that the object that you get will be a torus, in fact, a two-dimensional torus, and that the relevant transformation that will generate the sequence is this transformation. It's in the x-coordinate, it's just a shift by this irrational alpha, and the y-coordinate moves by an amount that depends on x, something called a skew transformation. And now if you just calculate the orbit of the origin, 0, 0, you get n alpha that you see easily, but you get this C of n as a second coordinate. So if you know the behavior of this orbit, you'll also know the behavior of this coordinate. Well, now we have a notion in topological dynamics, that's the right framework to look at this, of a minimal system. A system is minimal. That has two definitions, both of which are very natural from a dynamical standpoint. One definition is that it's minimal. Your space is a minimal closed invariant set. So if you have some subset that's invariant and also closed, then it's either empty or the whole space. And it's easy to see that this is equivalent to the following more dynamical description. A dynamical system is minimal if all orbits are dense, because an orbit closure, any orbit closure, will be a closed invariant set. So now, if we knew that this particular system was minimal, so then in particular the orbit of 0, 0 is dense, and in particular the second coordinate must be dense modulo 1. So that's our transformation of the problem. And indeed, the claim is that this particular system really is a minimal system. And it's true here for a topological reason, and that's where that M comes in, that condition that you add some non-zero amount, that ft is not actually periodic, so that there's as a transformation of the circle to the circle, it's an essential map, not homotopic to a constant map. And now the way that comes about is to study, well, if it's not minimal, then there are minimal sets. Just Zorn's lemma tells you there must be minimal sets. Now, what does such a minimal set look like? Well, whatever it is, it projects onto, it's an invariant set, and it projects onto, if I look at the x-coordinate of it, it'll project onto some minimal set down here. But this is a set invariant under rotation by irrational alpha. We'll assume that that's known, that when you irrational rotation, all orbits are dense. It's Kroneker's theorem. So it must project onto everything, and so therefore every point is represented. So every point will have something above it. And now the nature of this transformation, the fact that you move from one fiber to another fiber by rotation, tells you that in this minimal set, all the fibers have the same geometric structure. So either they're everything. If one of the fibers is everything, then all the fibers are everything, and then you do get the whole space, and that's actually what we're claiming. But if not, what would a minimal set look like? Well, again, it's not hard to show that it has this regular, if it's not everything, then you have some regular points distributed regularly in an equidistant k points on each of the circles. And they move around in some way that we don't have control over. But at any rate, it defines some sort of first homology cycle which moves in the horizontal direction non-trivially. Well, now we just look at what the given transformation does to the first homology, and we see that if the A is non-zero, then it cannot leave that cycle invariant. So I can't have an invariant cycle of this type, and therefore this could not have, if it really has this form, it could not be an invariant set, and therefore by reductio ad absurdum, we're led to the only other possibility that the minimal set consists of full fibers, and therefore everything. So this system is minimal. All orbits are dense, and that proves the theorem. But what I think this illustrates is that the fact that we're using some topological argument of this type makes it sort of highlights or underscores the fact that we really have to look at the system as a whole, and that you do get more information from that rather than looking at individual points or the individual sequence. And another example where this approach has worked is an extension of sort of a polynomial extension of the Samarati theorem on arithmetic progressions. Let me formulate that. This was proved by Bergelsen and Sasha Leibman. Suppose I have the idea is to generalize the notion of an arithmetic progression where you replace linearity by nonlinearity. So you have polynomials, some integer coefficient polynomials p1 to pk, which have no constant term. Pi of 0 is 0. And now the assertion is that if I have an arbitrary subset of the integers with positive upper density, in other words, the proportion there are arbitrarily large intervals in which the set has some fixed positive proportion, then there will be a polynomial progression corresponding to these polynomials, p1 up to pk, found inside that set of positive upper density. Something that started with van der Waals' theorem on arithmetic progressions, and this is sort of one of the advanced forms that it's taken. And as far as I'm aware, so far the only proof of this result goes by way of this setting up a dynamical system. In other words, seeing a certain sequence as arising in some dynamical context. Well, there the sequence that one looks at simply represents the set A. I have a sequence of zeros and ones, which are 1 on the set A and 0 off the set A. And then I see that I go to this canonical way of representing a sequence, seeing a sequence as being values along an orbit of some dynamical system. And so what happens is that there's so there is some dynamical system, and there'll be a set, basically some set B inside, and your sequence A really comes about by taking some point and looking how it visits the set B under the transformation, under applying the transformation. Now the fact that our set has positive upper density will correspond to the fact that this setup, this dynamical setup, can be chosen to be a measure-preserving dynamical system, or something that's studied in ergodic theory. And the issue of this type of configuration occurring in A, this type of configuration will occur in A if the set B here returns to itself in a manner that corresponds to the type of progression that we're looking at. That is, that the return times go according to these polynomials, that some point comes back after P1 of n steps, and then comes back again after P2 of n steps, and so on. And that will, if you can show that property for the set B, then you'll have this given property for the set A. Another way of formulating that is by stating that what you want to show is at a certain intersection, that for some n, an intersection of sets, the set of points in B that return after time P1n, that also return after time P2n up to Pkn, that measure is positive. Now that measure is an integral. It's an integral of a function that appears in this picture, namely where if I take the function f to be the indicator function of the set B, then this measure is just an integral of a product of functions. And if I want to prove that measure is positive, I want to show that integral is positive for some n. And the idea is that in ergodic theory, this becomes kind of a natural thing to look at. That is, you want to study instead of studying the object of this particular expression itself for single n, I mean, the lesson of ergodic theory is that you should average. You may be in a position to say more about the average than about the individual terms. If you can show that the average of these integrals is positive, then you're set. And this indeed is what happens. One is able to study what you might call non-conventional ergodic averages, studying these expressions. This f0 perhaps shouldn't be there, but you apply this transformation a certain number of times to f1, and then another transformation, a different power to f2, and so on up till fk, and you want to study that kind of expression. It's not the usual type of ergodic theorem that's studied in functional analysis. It requires a careful analysis of ergodic systems. But it turns out that one can study that average, and in particular, the idea that one can study that average was first really proven by, again, Birkhauser, by his polynomial ergodic theorem, which said that under certain conditions, some kind of mixing condition, this average is what you would expect it to be. It's simply the product of the integrals. In other words, that these expressions simply move independently and average out over the space. So that gives you hope that by an ergodic theoretic type analysis, you can study this expression. And that indeed is indeed what happens, and that's how Birkhauser and Liebman proved their polynomial Samarati theorem. Now, in all of these, in both of these situations, once you've got the information, you could sort of completely translate the problem to a problem in dynamical systems. once having solved the problem in dynamical systems, you have a solution to the number theoretic question. Now here are three open problems that are still open, and which I'd like to discuss and try to place them in a dynamical context and see if if some ideas can be presented for solving them. They're still completely open, each of these problems. One is the nature of the cube root of 2. The other is the nature of the transformation, really. X goes into the greatest integer in 3/2 x. No, I'm not asking. No, I'll explain it right away. But there's also nothing special about cube root of 2. But I didn't want to assume too much on the part of the audience. The last of these problems, the first and the last problems are fairly well known. The last problem is that studying the behavior of the fractional parts of a sequence like 3/2 to the n. Typically, you've got something growing exponentially, and it's much harder to study than what we had mentioned before earlier, the n squared alpha, which increases at a polynomial rate. So let's look at the first problem. So the cube root of 2 here, for our purposes, really is any algebraic number of degree bigger than 2. What is the problem? So let's say that a number is of bounded denominator class if I look at this infimum, this expression for all p's and q's, integer p's and q's, q not equal to 0, if the infimum is strictly bigger than 0, which is really saying that you cannot get too close to c using a rational. In other words, that your error will be bigger than some constant over q squared. For any number, you can show that you can get within, say, 1 over q squared, or better than that, but sometimes it's bounded. The amount that you can, the error in terms of q squared is bounded, and then we say it's a bounded denominator class, or BDC I'll call it, and it's unbounded denominator class if that infimum is 0. Another way of describing that is to take the continued fraction expansion of c. You have these partial denominators, a1, a2, and so on. Now, if the partial denominators are bounded, then it's a bounded denominator class, and it's unbounded, then it's unbounded. If they're unbounded, then you're in the unbounded denominator class. Now, for quadratic algebraic numbers, if I look at the expression qc minus p and simply multiply it by its conjugate algebraic number, then I get a rational number, which will have a denominator which will just depend on the number c. So that if this is not 0, which it won't be if the number is irrational, it'll never be closer to 0 than 1 over d. So for quadratic algebraic numbers are in the bounded denominator class. In terms of continued fractions, it's well known that in fact the continued fraction expansion is ultimately periodic, so that also makes it clear that it's of the bounded denominator class. Now, the remarkable thing in terms of what we know and don't know is that we don't know for a single algebraic number of degree bigger than 2 whether it's in the bounded class or the unbounded class, or whether perhaps some are in one and some are in the other. As far as I'm aware, nothing is really known about this. Now, there is a certain dynamical system which is connected with the continued fraction expansion, but it involves sort of looking at, say, c. You have to send x into 1 over x minus the greatest integer and 1 over x. This is a discontinuous transformation, and it's hard to see that you'll be able to make use of the algebraic nature of the number that you're looking at, so that this doesn't seem to be an appropriate way to translate the problem into one of dynamical systems. So let me try to describe another dynamical system that's relevant to this problem. So we take the space is the space of of two lattices in d-dimensional Euclidean space. So a point, well, up to a certain equivalence, which we'll define right away, a point consists of a certain two lattice that sits inside d dimensions. The lattice is two-dimensional, but it sits inside a d-dimensional space, and d is going to be bigger than 2. And now I introduce an equivalence relation where I say the two lattices are equivalent if they have generators, which is if I get one simply by dilating the other by a fixed constant. All right, then we can also, so we have L prime, and then we have L prime divided by this equivalence relation, and that's really the space that we're looking at. And now it makes sense to talk about a point being rational, because a lattice, I can talk about the vectors u and v being rational vectors. If u and v can be chosen as rational vectors, then I'll say that lattice, or the equivalence class of lattices, is rational. There is a rational point of this space. The space can also be represented, it's a homogeneous space of GLD, of the d by d matrices. And you get it by dividing just looking at what fixes a lattice, and you get a certain subgroup Q sub d, things that will fix a lattice. If this would have been SL2R instead of SL2Z, then this would be a parabolic subgroup. But so you have some arithmetic aspect of it and some algebraic aspect to it. And what we're studying really are orbits on this space. Orbits by choosing orbits that come by choosing rational elements. Take a rational A, take a rational matrix A. And now assume that that the largest eigenvalue of A, that there is a simple largest eigenvalue, larger and greater in absolute value than any of the other eigenvalues. Then you have the following relationship, which is not difficult to see. Nothing deep about this theorem. It's just a question of working things out. If I know that in the field that I get by extending lambda, the algebraic field, that if I knew that every number there was of the unbounded class, then what I can say is that every rational orbit, by this rational A acting on a rational point and looking at its powers, iterating it, this is unbounded. Of course, I have to stress the fact that X itself is unbounded. I mean, if you just think of lattices, I mean, the usual space that when one speaks of modular functions, the usual space here represents what happens if you take a unit vector as a fixed unit vector as the smallest vector in a lattice, and where the other positions are for the other generating vector of such a two lattice. And so with the normalization, this space is what's telling you what is parametrizing the different lattices for a fixed plane. Your two lattice lies on a certain plane. Space of lattices depends first of all on the planes, and then in each plane you've got something like that unbounded region. So in any case, our space is not bounded, and then the question becomes, what do orbits look like? And you can go in both directions. If rational orbits are unbounded, then you've got algebraic numbers with which are on the unbounded denominator class, and conversely. Now the thing is, why is this problem, now that we've converted the problem to a dynamical problem, why can't we solve it? The reason is that now different points are playing different roles. We're not asking something about every orbit. When we show that a certain dynamical system is minimal, then you're showing that every orbit is dense. And there clearly it's something that's tied to the system as a whole. Here we know that there are points that have bounded orbits. For every A, there are points that have bounded orbits. On the other hand, we know that almost all points have unbounded orbits, and sort of the question is, and this is a question which will recur here, whether do rational points behave like almost all points? I think the expectation is that they do. You know, unless there's a good reason that they should have a special behavior, which is what happens in dimension 2, you expect them to behave typically. And typically means that they'll have unbounded orbits. There's even some measure associated that you can try to show that the distribution or the distribution follows this measure, which would also show that the orbits are unbounded. Then another formulation which gives you perhaps less information, but it's a little bit neater from the point of view of the theory that actually Grisha Margulis will be talking about in the next lecture, the relationship between homogeneous spaces and Diophantine problems. Here we have a homogeneous space. Instead of looking at a single matrix A, we could take the subgroup, the algebraic subgroup of all matrices which commute with it. So that's a Q subgroup. And we apply that Q subgroup to a point defined over Q, lambda. And then what one expects is that those orbits are unbounded. Now, if that turns out to be unbounded, then you can show that certain algebraic numbers belong to the unbounded class. So much for algebraic numbers. And again, to emphasize that the reason these are problematic, you've got a dynamical system. However, no, so I believe, let's say, if I have to make a statement, I believe that all algebraic numbers which are not quadratic are in the unbounded class. The second problem is one in which it's sort of an easier model of this type of situation. And that's why I was interested in it. I want a simpler situation rather than some homogeneous space, simpler situation where you know something is true almost everywhere. Well, you're interested in what happens at points that you consider rational points and expect that they have typical behavior. Here, let me introduce a notation which I'll be using, talking about the m-adic integers. In this case, we'll be looking at the two-adic integers. So m-adic integers are inverse limits. You have the ring of m-adic integers, which is an inverse limit of these finite rings where I look at the integers modulo m to the k. M here doesn't have to be prime because I'm just looking at these as rings. Now, in particular, if we say we fix, for this discussion, we fix m equals 2, then we have the two-adic integers, and it's well known, every two-adic integer has this sort of canonical expansion, like ordinary integers do, except it goes from 0 to infinity. And in the topology of two-adic integers, 2 to the n goes to 0, so this sequence converges. The two-adic integers also represent certain rational numbers. Besides the ordinary integers, which are obviously represented here, you also have rational numbers like a third or a fifth or 7/11. In fact, any number with an odd denominator is located in the two-adic integers. This q intersect z2 hat. Now we can characterize the two-adic integers which are rational. Namely, they're exactly those for which their expansion is ultimately periodic. It's immediate. If you take something that's ultimately periodic and you write down the fact that one expression equals another, you conclude that the number, in fact, is rational. But it's not hard to go in the other direction also. If you have a rational number, you can show that its two-adic expansion is ultimately periodic. But now, instead of using the base 2, and the point about the base 2 is that it goes down to, that powers of 2 go to 0, the number 3 is a unit, and so on. For example, you could use 2/3 as a base. 2/3 serves exactly the same, plays exactly the same role as 2 from the point of view of ring theory, or even as topological, from the topological point of view. 2/3 to the n goes to 0. Expressions of this type converge, and every number in every two-adic integer has a unique expansion to the base 2/3 where the coefficients are 0, 1. And again, it's true that if something is ultimately periodic, then it has to represent a rational for the same reason as before. However, the other direction is not true necessarily. In other words, you could have things that are not ultimately periodic and nevertheless represent rationals. So let's see how one sees that. And the idea is to relate this expansion in the natural way to a natural transformation on the space of two-adic integers. You notice that whenever you have a sequence, you have the shift transformation. You can look at the sequence that you get by chopping off the first term. Now you can represent that explicitly as a transformation of two-adic numbers. See, I subtract from xi the first term, which will be xi of 0, then divide that by 2, and that would give me the rest of that would give me the shifted expression. So I can define a transformation t of xi, which is 1/2 of xi minus xi naught, or that's what we, for ordinary numbers, would call the greatest integer in xi over 2. Now you can do the same thing with 2/3, except now this time what it gives you is 3 times the greatest integer in xi over 2. And looking at applying those transformations is the same as applying the shift to the expansion. Good. Okay, great. Anyway, I'll put this on the other, but I'll still make use of the. So you have these transformations, which are in fact they preserve Haar measure, like the shift, and the shift preserves the natural product measure, and so these transformations, both these transformations preserve Haar measure, and the behavior of the sequence, is reflected by the behavior of the orbits. So the xi sequence and the standard two-adic expansion is ultimately periodic if and only if the t to the n, the t transformation, defines a finite orbit, because the shift transformation gives you a finite orbit. And the same thing with the xi prime n. The non-standard expansion will be ultimately periodic if and only if the other orbit, if the orbit according to t prime is finite. That's why t prime is in a way more interesting than t, because it's very easy to give an example where it's not going to be finite. And just working with ordinary integers, namely take any integer bigger than 3, and when you apply the transformation of, you take the greatest xi over 2, the greatest integer, and multiply that by 3, you tend to increase the number at an exponential rate. So, for example, if you start with 4, goes into 6, 9, and so on, and this increases, obviously it never returns, and so obviously you have a non-periodic expansion. What can you say? What does one find about these expansions? Now, I haven't really looked at this. I had somebody do some computer work on this kind of question, enough to make the conjecture, but can't say that I really studied it very, very, very much, or I don't know if it has been studied very much. But the belief is, and the belief that seems natural from looking at this, is that in fact the sequence that you get, you see, the x's are going to be 0 or 1 according to whether you get an odd or an even expression here. So for 4, it's two-thirds adic expansion is given by this sequence, which corresponds to the location of the 1s here. And the conjecture is simply that either, if you're not in the ultimately periodic situation, then what you get is a random sequence. Another way of saying a random sequence is to say that in terms of the orbit inside Z2 is to say that you've got an equidistributed orbit. If it goes into each open set according to the measure of that set. So that's the conjecture. And again, we're in the situation where we're expecting nice properties for certain orbits. They're definitely not true about all orbits, because these are both examples are Bernoulli transformations. And one knows for Bernoulli transformations that, first of all, almost all points do have equidistributed orbits. And that's the ergodic theorem. These are ergodic transformations. The ergodic theorem tells you that you've got that almost all points have equidistributed orbits. The question is, if a rational orbit does not have a good reason for not being equidistributed, like it's being finite. It's finite, it can't be equidistributed. But if as soon as it's infinite, is it necessarily equidistributed? That's a question we have for this. As for the previous question, we really have meaning I have really no clue for how one might go about it. The third problem is a little bit different. Still don't know very much about it. However, we can at least say that we have a clue, and that's what I would like to talk about in the rest of the time that Vitaly has thankfully given me. The problem is looking at 3/2 to the n modulo 1, or for that matter, you take any fraction p over q to the n modulo 1, and the question is, what is its behavior? Is it dense or perhaps equidistributed? Now, what's known is very little. It's known that the set of limit points has to be infinite, but that's all that's known, as far as I'm aware of, and the natural conjecture here is that, in fact, the set is dense. These sets are dense modulo 1. Now, the problem can be transformed. Again, you want to transform this to a dynamical system, and it's not immediately evident what the dynamical system is, because 3/2, you're looking at things modulo 1, and 3/2 is not a transformation modulo 1. Here you're first raising it to the n and then taking it modulo 1. It's not a transformation of the circle. This can be corrected by moving to a different group. Here it's indicated sort of briefly. If I want a group in which multiplying by 2 and by 3 are automorphisms rather than endomorphisms, instead of taking the integers, of which the circle group is the dual, take the integers, divide by, and take all rationals that have powers of 6 in the denominator. Then, and this group, multiplying and dividing by 2 and 3 are automorphisms, and so they will induce automorphisms on the dual group, which will be a compact group, and it's easy to see that that group maps onto the circle group because of the fact that Z is contained in the group that we're starting with. So now it'll turn out that there's a particular orbit, and if there's a particular point, and if we look at the orbit of that point in omega under powers of 3/2, if we knew that that orbit was dense, then the image in T would be dense, and similarly, if we knew if it was equidistributed, we would know that. There's another way of representing this whole thing as a cellular automaton. This group omega 6 can be more or less represented as doubly infinite sequences with entries between 0 to 5. If this were to stop at some point with zeros to the left, I would say that it's a real number expanded to the base 6. Except that it's really a solenoid in which you can move, in which you can have non-zero entries all the way out to minus infinity. This gives you a compact group which maps onto the circle group by simply looking at the second half of each expansion. It's a cellular automaton. The transformation which corresponds to multiplying by 3/2 is something which is a transformation that commutes with the shift. You determine each entry by looking at 3 entries, in this case, above it, and using you apply the same coding as you move along. And this is what gives you what's called a cellular automaton. Of course, the shift really corresponds to multiplying and dividing by 6. And 3/2 multiplying by 3/2 commutes with multiplying by 6. So here's part of the orbit of omega 0. Omega 0 turns out to be the point that has a 1 and everything else 0. So here's part of the orbit under 3/2, and this question is this orbit dense? Or at least is the right half of the orbit dense? Now, the full order, now what we have here, which we don't have in the other problems, is that there is another, the actual group that appears, the group of transformations appearing in the picture is larger than just the one transformation we're interested in. Namely, with any cellular automaton, you have the shift which commutes with the given transformation. So you have a sort of a two-dimensional group. You can move horizontally, you can move vertically in this picture. Or, if you like, you can multiply by 2, multiply by 3, multiply by 6, or multiply by 3/2. I mean, those are, ultimately, you've got a larger group of automorphisms. Now, if we ask, now we're interested in a certain point. And again, we're in a situation, it's a Bernoulli transformation. We know almost all points have dense orbits, but many of them don't. So the question is, on what grounds might we say that a particular orbit that a particular orbit is dense when we know that there are lots that are not? You have to know something, you have to be able to say something about the point. And what we notice here, let me say two things. First of all, going back to the full group, this full group of automorphisms, it turns out that this has a very nice property that every orbit here, when we're looking at this big group, we're close to the situation that we were in the torus we first started with. It's almost a minimal transformation. Not quite. There are finite orbits, but every orbit is either dense or finite, and you know which is which, because the finite ones are going to simply correspond to purely periodic sequences, and it's obvious that purely periodic sequences always lead to periodic sequences in a cellular automaton. Or torsion points have to move to torsion points, and so those will be finite orbits, but every other orbit is dense. So the full group, when you use the full group, it has large orbits. Okay, now what's special about this particular orbit is that if we look at one particular subgroup, the powers of 6, then this orbit closure is countable. It's infinite, but it's as small as it can be. It's simply a countable set. Any other manner of measurement, it turns out to be a small set. Well, now, this suggests, looking at general situation of commuting transformations, and here we come up with a problem that, again, we don't know how to solve, but it's a problem that can be formulated in quite a bit of generality, and it can either be proved in generality, or at least the generality would enable one to find counterexamples, and I haven't found counterexamples to it. So this is something called the Dimension Conjecture when you have commuting, expanding transformations. So suppose I have a manifold or some sequence space in which there's a natural notion, there are natural metrics and natural notion of dimension that attaches to these metrics. I'll say that a transformation is expanding if there's some bound delta, so that whenever 2 points are closer than that delta, and I apply the transformation to them, they don't get any closer. They stay at least as far apart as they were before. Then they can get very far apart and may come close together, but once they're close, they move further apart. Or they may stay the same distance. So examples of this is to take multiplication by p, where on say the torus, on the one torus. Or you can give various endomorphisms of higher dimensional toruses. Another example of this is to take sequences and simply look at the shift transformation on sequences. There are also cellular automata, that is, other transformations which commute with the shift, which are not the shift itself, which you can check are expanding transformations. So you have a rather large family of expanding transformations. The conjecture is that for expanding transformations, for an arbitrary point in the space, you can relate the double, if you have two commuting transformations, you can relate the double orbit closure to the single orbit closures by this dimension inequality. The dimension of the big one is less than or equal to the sum of the other two dimensions. Let me just say that this, already in the case of the circle, yeah, okay. Sorry. Already in the case of the circle, just take P and Q, multiplying by P and Q as your two commuting expanding transformations, and so there are several trivial cases. If x is rational, then all the dimensions in the picture are 0. If P and Q are related, so that both are powers of a single number, then it turns out that all the dimensions are the same. So again, the statement is true. Now, when P and Q are not related and the number is irrational, then it turns out that the full semigroup acting has a dense orbit. All those orbits are dense, which means that the dimension of the closure will be 1. And so the statement is that then it's not proved in that case. But if one thinks about it, one can see why it's plausible. The conjecture, the dimension conjecture in that case, reduces to this issue that the sum of these dimensions is bounded from below by 1. In other words, you can get each of them individually to be small, but not simultaneously, because you're somehow bounding the randomness in each of the expansions. You don't have that much freedom, and you don't have that much control. I'll mention mention a little bit later certain situations where we can verify this. This is, I don't know if one can say that if this were physics, we would consider this a theorem, just from the examples that are validated. But there are really very few examples in it of the general conjecture that are known. And at any rate, this kind of a statement can be a tool in showing, in proving that orbits are dense. Because in many situations, if you know that an orbit has full dimension, it already is necessarily, that the orbit closure is full dimension, it already is necessarily dense. And sometimes you are in a situation where you can say something about one of the orbits and this way learn something about the other. I see my time is up. I can't go into details about how this would apply to the 3/2 to the n problem. There, in fact, the transformations are not, as they stand, they're not expanding. But if you divide out by a certain subgroup, then they turn out, you do get expanding transformations, and you could get from this type of conjecture, you could get the information that's necessary to prove the denseness, at least, of these fractional parts. Let me just say two things. One is that if you don't have the expanding property, then you do not get this inequality. This dimension inequality need not be true. And the example is to take such a hyperbolic matrix, the 2, 1, 1, 1, and to take, say, multiplying by 10 as the other commuting transformation. By a theorem of Dani-Beren, the two of them together have dense orbits for all irrational points. Now take the point x, which lies on the contracting orbit, the contracting leaf of the sigma transformation. This point x, its orbit is countable and moves down to this point. And so its orbit closure would certainly have 0 dimension. On the other hand, I'm looking at it on a subgroup, and so under tau, it remains inside that subgroup, so the maximal dimension that you can get is 1, and the two of those don't add up to 2, which is the dimension of the full thing. And you can give many other examples of where you don't have expanding, where the inequality is not true. Let me just mention that this type of circle of questions is the origin of a certain problem that has attracted some attention. The question of finding what measures on the circle are invariant, say, under multiplication by p and by q, when p and q are not powers of the same number. I mean, the conceivable interest in that would be that if this program were to work for from the topological question, and you wanted to study something like equidistribution, you would then have to know what are the invariant measures for the full group. And that corresponds to the fact that we mentioned before, that the invariant sets for the full group or semi-group are trivial or everything. Okay, thank you.